So if we're looking at OH versus CO, what are we looking at to decide if we have a radical here? Valence electrons. So we have 6 plus 1 in terms of OH, that's 7, versus having 4 plus 6, which is 10. Specifically, what do we look for in terms of valence electrons? Odd numbers. So we have a radical here with OH, whereas we have an even number of valence electrons for CO. So that's not a radical in terms of what we know how to think about so far, which is using our Lewis structures to determine that. All right, so that's a little review from Friday. Let's move on to today's lecture. In terms of what we're going to be talking about today, we're going to finish up with talking about polar covalent bonds and finish up with discussing the idea of polar molecules. And then we'll move on to start talking about, well, we know how to draw our Lewis structures. How can we use those Lewis structures to think about the actual shapes of molecules? So first, thinking about our polar covalent bonds. What we had established is if we have a case where we have a covalent bond, but there's unequal sharing of electrons between the two atoms, namely because they have different electronegativities, what we see is we have a polar bond or a polar covalent bond where one of the atoms is going to pull away more of the electron density from that bond, giving it that partial negative charge, where the other atom is going to end up with a partial positive charge. In terms of thinking about, well, what do we call a covalent bond versus a polar covalent bond versus a purely ionic bond, it turns out that the distinction is a little bit fuzzy. It's not a clear line. But in terms of talking about things in general, and especially in thinking about problems for this course, what we're going to say is if you have an electronegativity or chi difference between the two atoms that is greater than 0.4 and less than 1.7, and we're talking about the Pauling electronegativity scale here, which is what's used throughout your book, if you have a difference in electronegativity anywhere in that range, we'll have what we call a polar covalent bond between those two atoms. So for example, if we compare the chi values for hydrogen versus carbon, we see they only have a difference of 0.4. 0.4 is not greater than 0.4, so we would not call this a CH bond. We would not say it's polar covalent. We would just call it covalent. In contrast, if we talk about a carbon-oxygen bond, now we have a chi difference of 0.8, so that is greater than 0.4, so we'll call a carbon-oxygen bond polar covalent. We can extend this idea of talking about these polar covalent bonds to thinking about an entire molecule. I'm sure you've all heard of the term a polar molecule versus a nonpolar molecule. And essentially, when we talk about having a polar molecule, what we're saying is that there's a net non-zero dipole moment within the whole molecule. So essentially, what we have to do is combine all of the individual bonds to think about the molecule as a whole. So let's take an example of carbon dioxide here, or CO2. Very soon in the lecture, you'll learn how to predict shapes based on Lewis structures. So you will quickly see that this is a linear molecule. We can think about the two bonds within it. There's two carbon-oxygen bonds, and we know that there is a dipole in that bond, which is going toward the oxygen. Remember, in chemistry, we always draw the arrow. We're always interested in what those electrons are doing. So if we draw in the bond dipoles, and you can draw these into your notes, you want to draw an arrow toward the oxygen in each case. But we're not just interested here in thinking about, do we have a polar bond? We actually want to know, in general, do we have a polar molecule?